Yes, hello everyone. My name is Minko. As Maxim mentioned, I'm an engineer in the Angular team at Google. Today I want to give you a couple of tips and tricks on how you can optimize your Angular applications. The practices that we're going to take a look at, although they are integrated as part of the Angular CLI, they are also something that you can take directly from this presentation and apply with any framework or even without one. So what we're going to take a look at today is network performance. We're also going to discuss a couple of tips and tricks on how you can improve the user's navigation, how you can reduce the number of bytes that you're transferring over the wire, and how you can efficiently deploy directly from the Angular CLI. So network performance. In the context of this specific presentation, we're going to define it the time that is required for the browser to fetch all the assets that are required in order to run the application. In order to improve the network performance of our app, we can do two things. Pretty much reduce the number of bytes, the number of kilobytes of JavaScript that we're sending or images, and also reduce the number of network requests. These are the very high-level optimizations. And it turns out that some resources are more expensive than others. If we ignore the latest advancements in parsing, because the browser can take a stream of bytes, and if it knows that this is JavaScript, it can parse it while it actually receives the payload from the network. If we ignore this, JavaScript is about 25 times more expensive than an image, because it needs to go through lexical analysis, syntax analysis. After that, the browser needs to compile it with its just-in-time compilation, and finally execute it. So JavaScript is a huge reason on why our applications are slow. And there are a couple of things that we have been doing for a while in the Angular CLI in order to make apps faster. Of course, minification and dead code elimination. These are techniques that have been a while outside of the open source community for a while now. As part of version 8, we also introduced differential loading, and we have code splitting for a while. Let us first talk about differential loading. Are you familiar with what differential loading is? OK. Are you familiar with differential calculus? OK, yes, this does not have anything to do with differential calculus, so that's the good thing. With differential loading, what we're going to do is produce two builds of your application. One for ES5 browsers which can run ECMAScript 5, and browsers which can run ECMAScript 2015. What do we get from that? So the ES 2015 browser, they use much more expressive syntax. This means that it is much smaller. And on top of that, they don't need redundant polyfills. For example, they don't need map, set, and many other polyfills which are introduced in ES 2015. By doing these two different builds, we're also introducing a reference in the index.html file to both ES 2015 and ES5, and the browser at runtime can figure out which is the right build that it needs to consume. So by very early benchmarks, we figure out that we can reduce your bundle size by 65 kilobytes from polyfills, and, well, actually it's 0 to more than 10% smaller bundles, depending on the expressiveness of the syntax that you're using. We got much more impressive results from a couple of projects, but this completely depends on the feature set that you use in your application. So just a reminder how differential loading works. We ship an index.html file to the browser with two script references. Depending on the feature set of the browser, it downloads either the legacy one, the ES5 one, or the ES 2015 bundle. From there, it just runs the application, and we get the user interface. That's the index.html file that we ship. Just two script tags, one with type module. Of course, there are a couple of complications here. For example, modules are always strict. So, for example, if you have a library that is not compatible with ECMAScript 5 strict mode, probably will not be able to use it with differential loading. And one with no module attribute. This is for legacy browsers which use ES5. Why did we choose differential loading instead of differential serving or any other fancy serving technique? So first, the deployment with differential loading, it is straightforward. All we need to do is take a bunch of static assets and move them to the CDN, and that's it. We don't need any complicated serving infrastructure where we are going to take a look at the user agent of the browser and figure out which script to ship from there. Also, there is a proposal for making differential loading first-class citizen. So at some point, we will be able to load an array of different ECMAScript versions, and depending on the feature set that the browser supports, the users will get the latest version possible for their user agent. So now let's talk about code splitting for a little bit. Code splitting is basically a more specific technique of larger set of practices called lazy loading. With lazy loading, we can just load assets when they're needed. Medium is a great example. We have a bunch of images there. When the user starts scrolling, when the images get into the viewport, the browser sends a request and download them. With JavaScript, we can approach in two different ways in order to introduce lazy loading. We can either use component-level code splitting or route-level code splitting. With component-level code splitting, we can suppose that we have a very heavy e-commerce platform, which is written as a single-page app. And we have a very complicated widget, something like Slack, which is 2-3 megabytes of JavaScript that the users can eventually interact with. And based on our statistics on how users are using our application, we see that only about 2 to 5% of users are actually getting engaged with this small chat widget that brings so much payload. So do we really need to introduce the chat widget as part of our initial load time? Probably no. Probably we can just delay it. We can just put a placeholder there, and when the user starts engaging with this placeholder, we can send a request over the network and download the associated JavaScript bundle. With Angular, we can take advantage of component-level code splitting using NGX loadable, for instance, or the hero loader. These are two third-party modules which allow you to implement component-level code splitting with the Angular CLI. It's pretty much straightforward, and I'll definitely encourage you to take a look at it, especially if some features of your application are not heavily used. Now, let us talk about route-level code splitting. With route-level code splitting, we can suppose that we have the following page here. So we have some newsfeeds, and we have a settings page. When the user is in the newsfeed, we really don't need the JavaScript associated with the settings page. This is something that the user can potentially need in the future. So the user is in the newsfeed. When they navigate to the settings page, right then we can send a request over the network to download the associated JavaScript module, in this case, the settings module, and bootstrap it in order to provide the settings user interface. This is a very powerful technique that I'll definitely encourage you to take a look at and take advantage of. With Angular, you can use it just by specifying in load children the module that you would want to load when the user navigates to a specific route. In Angular version 8, we switched load children from string syntax to dynamic imports in order to align better with web standards. So this is basically an automated migration that the Angular CLI is going to perform for you when you run ng update. So route-level code splitting is fantastic, but introduces one problem. What if our user has very poor network connection? What if their latency is a couple of seconds, let's say? We can simulate this by using Chrome DevTools, by updating the network throttling and setting, let's say, latency of 1.5 seconds. Now, when the user is in the newsfeed and they navigate to the settings page, they'll have to wait for a while before the actual transition happens, because they will need to download this bundle, and this may take a while. So we introduce all this enormous complexity in order to build single-page applications, so we can reach a very responsive user experience. And by using component-level code splitting or route-level code splitting, we introduce this delay, which decreases the user experience. And that's something that we definitely don't want to do. In order to improve in this scenario, what we can do is introduce prefetching as well. So with prefetching, while the user is in the newsfeed page, we can, in the background, download the settings page. We can cache it, so that when the user navigates to the settings page, we have it already in memory or on the disk. We can directly take it from there, and the browser can provide it. Problem with prefetching is that we don't know exactly what to prefetch sometimes. If we have hundreds or thousands of modules, do we want to prefetch all of them? Maybe we want to prefetch only a subset of these modules that the user is likely to use. But how do we guess what the user would want to use? Like, guessing what the user would want to use is sometimes not the most accurate strategy. We can try to predict what the user is going to do, but users usually use the application in a slightly different way. There are different heuristics that we can take advantage of. For example, we can prefetch all the visible links, or we can apply predictive prefetching, or prefetch on mouse over. Let us first look at prefetching the visible links on the page. There is a very powerful API called intersection observers, where, depending on the level of visibility of given element, we can get an event. With Angular, we can take advantage of it. So, for example, when the user starts scrolling the page, depending on the visibility of the individual links, we can prefetch only a subset of them. In this case, the team link becomes visible, so we prefetch the team link, and we keep going until we prefetch the contacts and about. This is the so-called quick link prefetching strategy, and we can take advantage of it just by installing ngx quick link, and from there, setting the quick link strategy as preloading strategy of the Angular router. So this technique is great. In some cases, it's not going to be the most powerful one. Imagine we have a page like Wikipedia, where from one page the user can go to tens or hundreds of others. We still hit this problem with overfetching. We may want to prefetch far too many bundles in this case. Maybe a more efficient strategy would be predictive prefetching. So on Google I/O 2018, with the Chrome team, we introduced a library called Gechev. Here's how Gechev works in short. After that, we're going to dig a little bit deeper. With Gechev, first, we're going to consume some analytics source. We're going to take a report from either Google Analytics or our custom analytics provider. We're going to parse the application and the route declarations, and we're going to map the actual route declarations to the URLs from Google Analytics or our reporting analytics provider that we use. Based on this aggregated information, we're going to build a machine learning model, which can be something as simple as a Markov chain or even a recurrent neural network, why not? Right after that, once the user navigates inside of the application, we can query the model, and depending on the page that the user is currently at, we can prefetch the chunks which are most likely to be used next. As a very simple example, here is how you can think about this. We have this app here, which is Wikipedia-like application. We can rank the individual links, and the higher the probability for the user to navigate to given a link, the higher the probability for us to download the associated JavaScript chunk is as well. Now, let us look how this works in depth. First, we're going to prefetch a report from Google Analytics or our custom analytics source. Here, the edges are the transitions between individual pages, and the nodes are the actual pages in our application. The thicker given edge is, the higher the probability for the user to perform a transition is as well. Now, how do we connect this to actual route declarations in our application? So our application looks something like this. We have route declarations which are defined in an array. We can look at the route declarations, and we can somehow try to map them to our Google Analytics report. How do we do this? Well, here on the slide, we see that we have /1, /a/1, and /a/2. And we also have the routing declaration a/id. So probably these map to each other, and we can associate the a chunk to the specific set of nodes from the Google Analytics report. So what we can do is just merge these together and think of them as a single node in our graph that we're going to use for prefetching. This means that Google Gechev parser is going to consider not only parameterized routes, but it is also going to take a look at our source code and try to execute it statically. It is going to look at the load children declaration here, and it is going to concatenate these strings as part of the build time. As soon as our route declaration does not depend on any runtime information, the Gechev parser is going to be able to evaluate our declaration and collect the metadata correctly. From there on, Gechev is going to invoke the model at build time with its Webpack plugin. So here is what it's going to produce in the end. As part of our main chunk, Guess is just going to introduce a very small library, a very tiny snippet used for prefetching of modules. And in each next chunk, it is going to include like small instructions on how to prefetch all the chunks which are likely to be needed from the current one. As you can see here in a.js, we are prefetching b.js with probability 0.3 and c.js with probability 0.7. Depending on the user's network connection, Guess is either going to prefetch any of these chunks or just ignore them completely. For example, with very fast network connection, Guess.js is going to be more aggressive towards prefetching. In other cases, it is going to be less. Yeah, so this is Gechev. I'll definitely recommend you to look at it. It's on GitHub, and it's already it has wide adoption in the Angular and in the React community as well with Gatsby.js. All right, so we discussed a bunch of fancy techniques here. We discussed how we can apply differential loading. We talked about code splitting. We discussed prefetching. We even included like some kind of data analytics or machine learning-driven prefetching approach. But this doesn't mean that our application is going to be fast over time. We can still include one node module, like just one import, and it can drag half of the node modules directory inside of our production bundle. So our application's performance can regress over time pretty easily this way. What we need to do is to introduce a set of metrics and monitor them on each code change. Performance budgets, they're a great chance for us to do this. Performance budgets are part of the Angular CLI since version 6. And I'm going to show you how they work in this very short video. So this is going to be a very fast example. We're going to go through a lot of things, so don't worry if not everything is too familiar to you. First, here we're building our app in order to set a baseline for how large our main chunk could be. Here it is 153 kilobytes, so now we can go to our workspace file, angular.json, and create a performance budget. The performance budget is just a JavaScript, a JSON object, where we're specifying what is the type of the budget. We specify what is the name of the chunk that we will want to create this budget for. And we're specifying maximum warning and maximum error values. This means that the build is going to throw a warning if our bundle is bigger than 170K, and our build is going to fail, excuse me, if our bundle is bigger than 250K. Now we just introduce a single import. And, well, we import from the wrong place. We import from Rx internal operators. So this is going to lead to growth of our bundle. Once we build our app, we're going to see that we are failing. So the size budget has been exceeded with a couple of kilobytes. If we want to fix this budget, we can just go to our app component, fix the import, and we're going to be back to normal. This is an excellent opportunity to introduce performance budgets of our continuous integration as well. Lighthouse, with the Light wallet, it already has great integration with performance budgeting. So this is something that could be a straightforward step out of our build pipeline. All right, so there is one more thing that we have been working on in order to make sure that applications are fast from end to end. We spent some time looking at Internet Archive and seeing what best practices most of the applications are following or not. And we noticed that about 27% of web apps are not using content compression. And this is very low-hanging fruit. We just need to enable gzip or broadly in our static server configuration. We also noticed that over 80% of apps are not using CDNs. And if we're building an application that should be consumed around the globe, this is a very low-hanging fruit that we should definitely take advantage of. We want to provide our static assets from the closest geolocation to our users. In order to provide best practices directly from the Angular CLI, we worked on ng-deploy. Here is a demo with Firebase. In order to use ng-deploy, you can just run ng-add angular/fire. From here, the CLI is going to install Angular Fire and a bunch of third-party dependencies, for example, the Firebase tools, and connect to Firebase in order to suggest which project we would want to deploy. Here, with fuzzy search, we can pick a project, and the ng-add schematics are going to edit our configuration. From here, we can run ng-run, the name of our application :deploy. And the Angular CLI is going to produce the most efficient build possible. It is going to run through ahead-of-time compilation in order to compile our templates to JavaScript. After that, it is going to perform tree shaking, minification, and a bunch of other optimizations. So finally, once the build completes, it is going to delegate the execution to Firebase, and Firebase is going to upload all the static assets to Firebase hosting. We're going to get a URL in the end so you can open our application automatically. So on ng-deploy, we're collaborating with a couple of big hosting providers, like cloud providers. We're working with Cloud, Google Cloud, and Firebase. We're working with Microsoft. They recently published the Azure ng-deploy package. And with Zeit, I think today, Zeit published Zeit/ngdeploy, so you can already take advantage of this. It will be amazing if, actually we're working with community members on introducing ngdeploy to GitHub pages, which is a great feature. Like we're getting free hosting for like amazing CDN for free there as well. That was pretty much all of it. In order to make a very quick summary, let us just very briefly discuss what we talked about. We discussed on how we can reduce our bundle sizes by using differential loading, producing 2 builds of our applications. One for ES5 browsers and one for ES 2015 browsers. We also discussed code splitting and how we can speed up page navigations when we introduce route-level code splitting. We talked about predictive prefetching with Gechev and NGX quick link. After that, we discussed how we can automatically deploy from the Angular CLI by using the ngdeploy command. And of course, we mentioned performance budgets, which help our performance to not regress over time. That was everything. Thank you very much for your attention.